Okay. Okay, so it is time now. So today is going to be my last day in this lecture. So basically, it will be the end of my lecture for this semester. And next Monday, we will start a new material with okay. But before we begin this part of the lecture, so we will quickly cover the rest of the topics that we have left. So I told you earlier that from Monday, we have something that the previous two slides from lecture 8. So let me cover this real quick. Okay, so for this exercise 5, I want you to calculate the energy of this reaction right here. So how we do this problem? The thing is, the energy it's related to E naught of the cell through this relationship that we covered earlier. Okay, the energy equals minus m times f times E naught of the cell. So I want you to calculate the energy for this reaction. And this is what the problem gives you. It gives you E naught of 1/2 cells. Okay? And basically, the way you do this is you have to find another half cell that is compatible with this one. So basically, it is going to be this half cell right here, O2 plus 4H plus 4 electron goes into water, where the E naught is 1.23 volts. Well, the thing is, NH4OH is basically ammonia with water. So, how I do this problem is I can essentially just ignore the water and ammonia. They will basically cancel out and this will give me ammonia right here. So when you add these two half cells together, this is going to be the final reaction that you have. Okay? So the E naught of the oxygen half cell is plus 1.23 volts, and the E naught of the ammonia half cell is 0.09 volts. So which one will be my anode and which one will be my cathode in this case? The ammonia half cell or the oxygen half cell? Which one will be the anode and which one will be the cathode? Which one? The ammonia will be my anode, right? Because it has lower E naught value, right? So my oxygen half cell, which has higher value of E naught, will be my cathode. Right? So I can figure out the value of E naught of the cell by using this equation right here, E naught of the cathode minus E naught of the anode, which works out to be 1.14 volts. Okay? And now you can use this number to calculate the G naught by using this equation. The G naught equals minus n times f times E naught of the cell, right? So E naught of the cell is 1.14 volts, so you can plug that in. What about F? Well, F is a Faraday's constant, which is 96,500 coulombs per mole, right? What about M? Well, as I mentioned, M is the least common multiplier on the LCM of the number of moles of electrons of these two half cells, right? So you can see that for these half cells, there's 6 electrons, and here there are 4 electrons. So the LCM of 6 and 4 is what? The LCM of 6 and 4 will be 12, right? So we use n equals 12 in this equation right here. So when we calculate for the final answer, then the G naught will be equal to minus n times f times E naught of the cell. So it's minus 12 times 96500 times 1.14, which gives me the answer of minus 1.32 times 10 to the 6 joules per mole. Remember, what you got from this equation will be the units of joules per mole. But the energy naught is usually expressed in kilojoules per mole. So I divide this number by 1000. So I got minus 1,320 kilojoules per mole. So you can see here that this number is negative. What does it mean? Does it mean that this reaction is spontaneous or not spontaneous? Is this reaction spontaneous? looking from the value of the genome. Is this reaction spontaneous under standard state? Spontaneous or not spontaneous? Spontaneous or not spontaneous? Spontaneous, because you have a negative the genome right here, right? Okay, or alternatively, if the ENOT of the cell is positive, it corresponds to negative energy, so you can always say that reactions in galvanic cells are always spontaneous. Okay? And for this exercise right here, I want you to calculate the ratio of the concentration of zinc 2+ and copper 2+. That makes the following galvanic cell become spontaneous and amplified. We see. Of course, I'm going to use the next equation, okay, where the E cell equals E naught of the cell minus RT over NF times the natural log of the reaction quotient. Okay, so what's the reaction quotient? Well, looking at this equation, so you only take the aqueous species, right, the zinc and the copper. So this is your reaction quotient right here. I don't care about the salts, just the aqueous phase. Okay, so I want to find this ratio when E cell equals 0, right? Because, well, that's when the reaction starts to become spontaneous, right? So basically, it's spontaneous when E cell is greater than 0 or delta G is less than 0. They are always reversed because the G is minus n times F times E cell. Okay, so I have the condition right here. So, sorry, E cell has to be greater than 0. So this term has to be greater. So let me work this out so that you don't get confused. Okay. So the E cell is greater than 0. It also follows that E naught cell minus RT over NF natural log of zinc 2+ over copper 2+ needs to also be greater than 0, right? Because this thing and this thing are the same. Okay, so E naught cell, sorry, has to be greater than RT over NF times the natural log of Q, let me write that for short, okay? Which Q is just this guy right here, or RT over NF times the natural log of Q is less than E naught of the cell. Okay, what's E naught of the cell, by the way? Well, we have the classic zinc and copper galvanic cell, right? So E naught of the cell is basically 0.34, which is the one for copper, which is the cathode, minus 0.76 volts. That's for cathode. Sorry, zinc anode, right? Which works out to be 1.110 volts. So this is the one you plug this in, right? So Q has to be less than the exponential of RT times E naught cell, sorry, NF times E naught cell over RT, right? And this Q is the ratio that we want to look at, okay? So this is the threshold. The ratio needs to be less than the value on the right for this cell to be spontaneous. Okay, so let's work out the number on the right hand side. It's E raised to the power of n equals 2, right? Because each half cell has 2 electrons, so basically n equals 2 in this case, times F times E naught cell, which is 1.10 over 8.314 times the temperature, if not degree C, which is 298.15. So if I work out this number, I found out that the answer would be, let's see, which is quite a lot. So it's 9 times 2, 6 times 10 to the 55. Okay, that's quite a lot of number. No, sorry, I think I'm wrong. It's 298, sorry. I think it's up in the value incorrectly in my calculator. Well, still quite a large number. It's actually 1.57 times 10 to the 37. Okay, so that's the answer right here. Why doesn't it show? Okay, there it is. 1.57 times 10 to the 37. Okay, so basically, if the ratio of zinc and copper is lower than this reaction will be spontaneous at 25 degrees C for sure, right? And normally in the cells here, it's usually lower, okay? Much lower. So that's good enough. Okay, so those are the problems from the previous slide. So let's actually now talk about the last lecture slides. Okay. Okay. Let me turn this on for a moment. Okay, so now this is just a review, basically. So this was the equation that we covered from the previous section. Okay, so we talked about how the E cell or E naught cell are related to the thermodynamics parameter. So you can see here that they are all related to delta G and delta G naught. Okay, where delta G is just minus M times F times E cell. And delta G naught equals minus M times F times E naught of the cell. Okay, therefore, you can see here that since we learned from the thermodynamics chapter that delta G naught equals minus RT times the natural log of the equilibrium constant. So you can see that E naught of galvanic cells are also related to the equilibrium constant as well. Okay. And another thing that we found is what we call the Nernst equation, where we derive Nernst equation from delta G equals delta G naught plus RT times natural log of the reaction quotient, right? So as we work out using this relationship that we had, we found out the Nernst equation to be E cell equals E naught cell minus RT over NF times the natural log of the reaction quotient. Okay, so this then is the number of moles of electrons transferred in the balanced redox equation, which can be calculated from the least common multiplier of the two half cells that we normally do when you balance your redox equation. Okay, and this F is the Faraday's constant. Okay, which is the charge of 1 mole of an electron. Okay, so this is what we covered from the previous lecture. Okay, so let's move on to the next slide. There are some other problems that we want to get used to this topic because it can be hard because this topic combines both the galvanic cell aspect of this chapter and also the thermodynamic aspect from the previous chapter. So better study up for your final, okay? The average scores, as I announced on Tuesday, wasn't so spectacular. So I really encourage you to study a lot so that you can tackle the final accordingly. Okay, so let's take a look at the exercise here. Without looking at the EMA table, I want you to calculate EMA of the following half cell. Okay, given that delta G naught F of H2 gas is 0, delta G naught F of H plus is also 0, delta G naught F of lithium also 0, and delta G naught of lithium is minus 203.8 kilojoules per mole. Okay, well, if you look at the table, I think the number, the value of EMA of this thing is about minus 3 point something volts. Well, let's see if we can do that by calculation here. Okay, how do I know the EMA of this cell? So basically, what I do is I plug this in with the SHE, right? What's the SHE? We talked about that yesterday. What is the SHE? The sheet. This thing is the standard hydrogen electrode, right? Where we know that the voltage is 0 by definition, right? So we plug this in with something like this: 2H plus increase plus 2 electrons goes to H2 gas. Okay, so this is we plug in with, and we know, sorry. We know the EMA of this half cell is 0.0 volts. Okay, that's what we know. So EMA of the cell is going to be EMA of the cathode minus EMA of the anode, right? Which one do you think will be the anode in this case? Which one will be the anode? Definitely, the lithium will be the anode, right? Even though I don't know the value, I can just remember roughly that it's minus 3 something. So that's a very, very low number, right? Since that's a very, very low number, much lower than 0, of course, it's any number anyway. So lithium half cell will be my anode, right? Whereas the SHE, the sheet, will be my cathode for sure, right? So this thing equals to 0.0 as EMA of the cathode, which is the EMA of the SHE, right? Minus the EMA of the lithium half cell, right? So basically, EMA of the lithium half cell, which is something you want to calculate in this exercise, in this example, will be equal to minus EMA of the cell. Okay, so what we do to figure out EMA of lithium is to find out EMA of the cell and take the minus sign in front of it. Okay, so how do we find EMA of the cell? Well, from the previous slide, we know that delta G naught equals minus NF EMA of the cell, right? So, of course, you can calculate EMA of the cell from delta G naught, right? And how do you get delta G naught of the total reaction? Well, you can see here, these are the things that I gave you, right, from the previous chapter. I gave you the Gibbs free energy of standard Gibbs free energy of formation of everything, right? So basically, you can calculate delta G naught of the combined reaction. If you combine these two half cells, what do you get? What you got will be this, right? You will have 2 lithium plus 2H plus goes to lithium plus H2. This is what you have. as a net equation when you combine the two answers together, right? I want to calculate the G of this reaction. The G naught, sorry, how do I do that? Well, the G naught of this reaction will be what? It will be 2 times delta G naught F of lithium plus delta G naught F of hydrogen, right? Minus 2 times delta G naught F of lithium plus 2 times delta G naught F of proton, right? So you can see here that delta G naught F for H2, Li, and H plus, they are all 0, right? 0, 0, and 0. So basically, my delta G naught will be just 2 times minus 293.8, which is minus 587.6 kilojoules per mole, right? Minus 587.6 kilogram. Okay, minus 587.6 kilojoules per mole. Okay, so that's it for now. I got my delta G naught. So I will use this delta G naught to calculate for my E naught of the cell, right? So let me change the color. Delta G naught equals minus NF E naught cell. So E naught cell will be minus delta G naught over N times F. Right? Here we go. Sorry for the math. Okay, minus delta G over NF. So it's minus what? 587.6 times 10 to the 3 power. The unit of this thing is joules per mole. I have to convert kilojoules into joules first. Divide by N. What's N? What's N? Well, look at these two answers and look at the number of electrons transfer. Can you tell me what's N? What's N? What is N? 1 or 2? 2, N is 2, because it's the least common multiplier to divide 2, right? 2 times F, which is the first constant, 96500. So when I work this out, okay, so I got this number to be minus 3.04 volts. Okay. Well, sorry, the G naught here is actually minus, so it's minus. The answer is actually E naught cell equals plus 3.04 volts. Okay, don't forget about the sign. Okay, my little G naught was already negative number. So you have minus here from this, and then combine with another minus sign. So my answer here for E naught cell is positive. It's plus 3.44 volts. But I didn't ask for E naught of the cell. I asked for E naught of the lithium cell, right? But when I connect with this SHE, I found that out. The E naught of the lithium cell is just minus E naught cell, right? So E naught of lithium is just minus E naught cell in this case. So it's minus 3.44 volts. That's my answer. Okay. So if you want to convert this, you can take a look at the standard reduction potential here. And then you know that this is the number that you should get. Okay, it's actually around that number. So this is how I calculate from this example. Okay? Any questions? All right, looks like that's not any questions. So let's take a look at another example here. A piece of magnesium metal weighs 1.56 grams is placed in the silver nitrate solution with 100 milliliters and 0.100 molar at 25 degrees C. I want you to calculate the concentration of silver ion and magnesium ion at equilibrium. Okay? How do I do that? Well, the thing is, you want to know the equilibrium constant of this reaction first, right? So what is this reaction by the way? So let's figure this out. Magnesium and silver, right? So this is what we have. 1/2 cell will be magnesium solid goes to, sorry, let me write out the reduction half cells first. So it will be magnesium 2 plus aqueous goes 2 electrons, goes to magnesium solid. And another reaction will be silver plus 1 electron goes to silver metal, right? Now tell me, what are the ions of each half cell? Go look at the table. There's a table in this slide too, in the next part of this page. So go look at the table and tell me what is the ion of each half cell. Tell me what's the ion of each half cell. Let's talk about magnesium first. What's the ion of the magnesium half cell? 2.1, 2.37, right? What about silver? I guess it's plus 0.80, right? I remember. 0 plus 0.84 volts. So now tell me, if I connect these two half cells together, which one will be my anode? Magnesium. Mg. Why? Because the ion is lower, right? As I told you, if you connect two half cells together, the one with lower value of ion will always be your anode, right? And the one with higher value of ion will always be your cathode. Always, right? Always the case in the galvanic cell. So the magnesium half cell will be your anode, and the silver half cell will be your cathode, right? So that's how you look. So what is the ion of the cell? Ion of the cell is ion of cathode minus ion of anode, right? Which is 0.80 minus 2.37, which is plus 3.17 volts. Okay, so that's my ion cell right there. But why the heck do I calculate this? I think the part has something about equilibrium, right? Like I said, this thing has the initial concentration, but I don't know the real constant of this reaction. So you have to find out the equilibrium constant first. Okay? So how do I find out the equilibrium constant? So things are actually related to this expression right here, delta G naught, right? I knew it from the previous unit that delta G naught equals minus RT times the natural log of the equilibrium constant, right? But delta G naught also has another relationship to the ion of the cell, which is minus N times F times ion of the cell, right? So these two terms are equal, right? Minus NF ion cell is equal to minus RT times the natural log of the equilibrium constant, right? So now I know what M is, I know F, I know E on cell, I know R, I know T. Of course, I can calculate my equilibrium concept of this reaction. So K will be the exponential of MF in cell over RT. Okay, so if you plug in those numbers, you have, well, K equals exponential. What's M? What's going to be my M? Looking at these two answers, I think you can tell me what's M. The LCM of one electron and two electrons. What's M? What's M? 2, right? The least common multiplier of 1 and 2 is 2. So I can plug everything in just like that. And my value of K will be quite high actually. Yes, it's very high. So it will be 1.55 times 10 to the 100 whole second. That's a very large number actually. So since K is very large, well, you can try using the IC table that I taught you with the equilibrium chapter to find out the equilibrium concentration. But with this large equilibrium constant that you see here, I expect that you won't have any or barely the reacting step. You will be left with mostly the products at equilibrium. So what will be my product anyway? Well, my product will be what? The silver will be more. So you get more silver in this case, right? Magnesium will just grow and then you get silver as a result, right? Because silver is the cathode. So silver plus got reduced into silver, right? And then all the magnesium you put in will be mostly dissolved because of the very large equilibrium constant that you see here. Okay? Any questions? You can try and verify whether my work is wrong by just doing ICE table as I taught you. Try that yourself at home and then see whether if what I say was true or not. Okay? Let's move on. All right. So this is another, this is our table again for the stack reduction potentials. Well, we looked at this table yesterday. Monday. So I want to look at it again, right? So now tell me, looking at this table, what is the best oxidizing agent? According to this table, what is the best oxidizing agent? Well, the answer is actually on the slide. I should have told you. What is the best oxidizing agent? Fluorine, right? F2. What about the best reducing agent? Lithium. How do I know? Well, I told you last lecture, right? That the way you look is you have to look upward for the stronger oxidizing agent and look downward for the reducing agent, right? The more specific detail was actually in the last lecture. I haven't put the video on that, but I will put the video of the last lecture combined with this lecture, so maybe you can review and I'll let you know once I post all the videos in the page. Okay, so look at this table again because we'll come back and consult this from time to time. Okay, so let's actually move on. Now, I want to talk about the applications of the galvanic cells, right? Since galvanic cells are spontaneous by nature, by definition, So the reactions inside the galvanic cells are spontaneous by nature. And because they're spontaneous, they also produce voltage differences between the two ends of the galvanic cell, right? Since they produce electrical voltage, what will they produce when you connect the galvanic cells with electrical wire? So you have electricity flowing through the wire, right? That's why the main application of galvanic cells are for batteries, right? So you can see here that in this slide, this is the most common batteries that you see at home, right? The alkaline batteries, right? So this is mostly used as the AA, AAA batteries that you can get at any convenience stores, 7-Eleven, etc. And you can get that for cheap too. But how does it work? So you can see that on the anode, the reaction here is actually zinc goes to zinc 2 plus, right? And on the cathode side, you have the manganese 4 oxide, B oxides into manganese 3 oxide, okay? And then you also have ammonia as a product. So basically, you can see that the overall reaction is zinc reacted with the ammonia ion and the manganese 4 oxide goes to zinc 2 plus and ammonia and manganese 3 oxide. This reaction is not reversible anyway, so you cannot really recharge this kind of battery. So that's why when you use up this type of battery, you have to throw it away in a bin. Okay, because when the power runs out, we need to throw it away. There's no way you can recharge this type of battery back. And how does it work? So basically, if you can slice into these types of battery, what you see here is that this thing is labeled as positive, and the bottom of this battery is labeled as negative N, right? What is it actually? So the negative end of the battery actually corresponds to the anode, right? Because the direction of current flow is always the opposite of the direction of the electrons. That's physics for you. You learned that from high school. The direction of electrical current is opposite to the flow of the electron, always, right? So electrons flows from anode to cathode, right? Because anode is right here and cathode is at the top. So electron flows from the bottom to the top. But the actual current flows from top to bottom, flows from positive voltage to negative voltage, right? That's physics. Currents always flow from high voltage to lower voltage. And you can see high voltage on the end with positive, right? And then you can see here that in this type of battery, normally you have zinc in the bottom because zinc acts as an anode, right? What's my cathode? My cathode composed of manganese 4 oxide, right? So basically, this rod right here is the rod of the graphite, which is the electrode, and then you have these layers of zinc and ammonium, and then you also have the layers of manganese oxide that covers the graphite cathode, providing a source for the electricity for the cathode side. Okay, so that's how this type of battery works. That's why we call it alkaline batteries, because it exists in the basic condition. Okay, so there are also other types of batteries as well, right? Not only the alkaline batteries. You may also have this type of battery as well, right? So where do you mostly find this type of batteries? Where do you mostly find this type of battery? Where do you mostly find this type of battery? In where? This type of battery is found in which device? What kind of device? In where? In your watches, right? Your watches, in the remote controls, or in some car keys. nowadays, right? They use this type of batteries, right? Mercury battery. They are very small and very thin. Okay, so you can see here that they also use zinc as the anode, just like the previous type of the battery. But what are the cathode? Well, the cathode is the mercury to oxide, and they got reduced into mercury, right? So what's the structure anyway? So you have the surrounding, the coating of the zinc. So basically, the outer end is the zinc being covered like that, and the cathode is connected to the solution of mercury to oxide and also zinc to plus, right? And then as reaction occur, this solution mercury will got reduced into the mercury metal, and then you have the electricity flowing around in this case. Okay. Then there's another type of batteries that's common in your cars and in some of devices, the lead acid batteries. Of course, this is most common in your car, right? Because without this, can you start your car? No, right? Without this, your car won't start at all. You need this in your car. And what's the best thing about this type of battery compared to these two that we mentioned? Is that you can recharge this battery, right? So basically, during the phase of discharging means gives electricity, right? So during the discharging phase, what happens? Well, what's in the anode? The anode is the lead metal, right? So the lead metal got oxidized into lead sulfate, right? Well, what about the cathode? The cathode is lead for oxide being reduced also into lead to sulfate. Okay? So this is the phase where your battery is working, giving your electricity, right? So, of course, you can see that these plates are mostly lead, right? And then you also have the positive plate with lead to oxide, lead for oxide, right? So you have all these plates inside your battery as the electrode. And then you have these concentrated sulfuric acid as the electrolyte solution that conducts electricity between all these plates in the batteries, right? And of course, I told you that you can recharge this battery. So when this type of battery dies, you can recharge. And what happens when you recharge this battery? Well, the reaction just gets worse, right? So you can see that this is now the cathode, right? The previous anode now becomes a cathode because it's where the induction reaction occurs, right? And the previous cathode now becomes an anode because that's where the oxidation reaction occurs. So when you recharge this type of battery, the anode and the cathode switch roles, right? Because the nature of the redox reaction changes for both half reactions. Okay. And of course, the last type of battery I want to talk about is the most famous one nowadays. Where can you find this type of battery? Where can you find this type of battery? It's around you. Where can you find this type of battery? Tell me. Where can you find this type of battery? Where? It's very common nowadays. Where do you find this type of batteries? In your phone, in my iPad, even in my watch, pretty much everywhere in all portable devices, right? The lithium-ion batteries. Even now, they found a way into your cars as well, like the battery electric vehicle. Things like Tesla vehicles, something like that, right? So this is what happens in the lithium-ion battery. So you can see that in the anode, lithium is being oxidized into lithium plus. That's quite common, of course. And what about the cathode? Well, the The cathode is the lithium plus the cobalt or oxide, all being reduced into this product right here. And of course, for this type of battery, you can also recharge as well, right? And the relation got reversed as you recharge this battery. Okay, so each cell is 3.4 volts because lithium is actually one of the most it has one of the most negative ion among all the answers. Okay, so the reason why we put the lithium ion battery in your phone is because the weight is very small, right? Where is lithium in the periodic table? Lithium is just the third element in the periodic table, right? So it's very, very light compared to things like lead or iron or zinc, etc. So lithium is really, really lightweight, right? So that makes the weight of the battery far lighter than other types of batteries. Okay, so that's how you can make all these things a very, very low weight, right? So that's why this thing is very lightweight. You can carry this for around. Imagine if the battery of your phone is made of lead, you can't even lift this phone. Hey, it will be like pretty redundant. It will be very, very hard to use. Okay, lithium ion makes all these devices lightweight. Okay, and not only that, the last type of galvanic cell that I will talk about is the fuel cells, right? So fuel cells are quite different from the batteries. How they differ? Well, fuel cells are essentially electrochemical cells where you put in traditional fuels, like traditional fuels such as what? Such as gasoline, right? What's gasoline? It's something you put in your car or your motorcycle when you want to go somewhere, right? So instead of burning traditional fuels like burning gasoline, burning hydrogen, instead you use these fuels in the electrochemical cell by reacting all these fuels, things like gasoline or hydrogen, with oxygen gas, but you don't burn them outright. But you react them in electrochemical cell just like this. For example, here is the example of the hydrogen fuel cells, right? So you just basically put in hydrogen on this side, you put in oxygen on this side, right? And then these electrodes, anodes and cathodes absorb both gases, and then they start to react electronically. So basically, all this it will give off electron in the anode, and then the cathode will eventually receive electron completely in the electrical circuit, and then you have the net reaction of just hydrogen plus oxygen becomes water, and then the output is the electrical energy, right? So the applications of hydrogen fuel cells are also in the automotive industry, where we use this in some type of cars as well. So you can fill in hydrogen, and then they use the fuel cells reactors, where the hydrogen will react with the oxygen inside the reactor and produce the electricity that we use to drive the motor of the car. Okay. So those are the types of galvanic cells. So these applications are mostly used for something that gives you electrical power to do work. Okay. So another thing that involves galvanic cell is the corrosion, right? This is not like an application we talked about in the previous slides, but it's something that you don't really want to occur, right? What's corrosion? So corrosion is when your metal being degraded away in nature, right? For example, when you have the iron metal that sits outside for a long time, what happens? When you have iron bar that sits outside for a long time, what happens to that iron bar? When you have the iron bar that sits outside for a long time, what happens to the iron bar? What happens to iron? when you let it stay outside for a very long time, what happens to iron? What happens? You can answer in time if you want to. What happens to iron when you put that outside for a long time? Yeah, and in English it's rust, so it rusts. Basically, it rusts. Yes, it rusts. So you know what actually happened, right? What does rust do? Well, it doesn't do anything, but it breaks your iron as an material, right? So how does rust form on your iron? Well, basically, if your iron metal is exposed to the atmospheric humidity, right? Of course, our atmosphere contains some water, right? So you can have water on the iron surface, so you can have this process, this spontaneous process going on, where your iron will be the anode which rusts away, right? So iron will lose electron to become Fe2 plus, or and then eventually to Fe3 plus, right? And then inside this drop of water, there are also oxygen gas dissolved in water, right? So that basically, as this happens, iron and oxygen reacts in the droplet of water in your iron, right? So when you combine this anode with this cathode, you have a spontaneous reaction going on, and it becomes a sort of galvanic cell. So for this spontaneous reaction, ions rust away, right? So you have this rust form. So these ions, Fe2 plus and Fe3 plus, can react further with the oxygen to form what we call the rust, which is usually things like Fe2O3 or something like that. This thing is not very strong, they are very brittle, and it degrades your iron as a material, so it might make the structure that made of iron fail eventually because they lose the strength to hold weights. Okay, you don't want that to happen with iron. Okay, but you can definitely prevent rust from occurring in your iron as well. So by the knowledge of the galvanic cell or the knowledge of the redox reaction and all those standard reaction conditions, you can try to prevent rust from happening. How do you do? Well, one process, one way that you can prevent rust is called galvanization. What's galvanization? Well, galvanization is a process where the metal is coated by a protective layer that rusts away before the metal, right? For example, iron, which we don't really want to rust, can be coated with zinc, right? Why? Why we coat iron with zinc? Because zinc will rust away before iron. So that's why we typically coat iron with zinc, because zinc will rust away before iron does. So by the time that all zinc rusts away, your iron will start to rust. But we have enough zinc to last your iron structure for quite a long time, hopefully. Okay? So, well, I just say that zinc rusts away before the iron. How do I know that? I know that because of this table. Okay, let's wait for this table to here. Okay, I know that because of this table. Now, I want you to look at the EMA of the zinc half cell and compare that to the iron half cell. Okay, where's the EMA of the zinc half cell? Well, right here, right? Minus 0.76 volts. That's the EMA of the zinc half cell. Come on. Okay, so that's the EMA of the zinc half cell. So what's the EMA of the iron half cell? look about 2 lines above zinc, right? So if you compare these two half cells, the iron and the zinc half cells, which one will be a better reducing agent? Iron or zinc will be a better reducing agent. Iron or zinc will be the better reducing agent looking at these two half cells. Zinc, yes, why? Why zinc? Because it has a lower EMON value, right? So with lower EMON of that half cell, it means that zinc wants to have the oxidation reaction is more likely to happen with zinc before iron, right? So that's why when you coat your iron surface with zinc, zinc will rust away before iron because it likes to lose electron better than iron, right? So zinc will have to rust away completely first, and then your iron will start to rust. That's why you can coat your iron with zinc. Not a problem, because zinc will rust away first. Well, if the cost, if the cost actually supports, so you can also coat your iron with some other metals too, right? You can also coat with aluminum too, right? Because aluminum also has lower EON than iron. You can also coat your iron surface with aluminum, same thing. You can also coat your iron with magnesium, same thing, because it rusts away from the surface before iron does. Okay, so that protects your iron structure. Okay. Another method that's way for this to come up. So besides galvanization, there's also another way you can protect your iron structure. You can also do it using cathodic protection. It's a very similar principle, right? So basically, with galvanization, you just coat the surface with the metal that rusts away before iron, right? It's very similar here. So you connect your iron with the electrical wire to the metal that you know will rust away before iron as well, right? So for example, if you have an iron tank underwater, if you don't connect that with some other metals, of course, eventually this tank will rust away underwater, definitely, right? But how can you prevent this iron tank from rusting? Well, you can connect the electrical wire or the conductor with some metal that will rust away before iron, right? In this case, magnesium. So what will happen is that magnesium rod will just rust away before iron does, because magnesium half cell has the lower EON than the iron half cell. So let's say this, you want to use the metal with the lower EON compared to iron for this to be effective, right? So in this case, magnesium will rust before the iron does. So when the magnesium all rusted away, then you have nothing to take your iron tank now, and then your iron tank will start to get rust away over time. Okay, so that's the principle of how you protect your iron from rusting. So you can also connect that by using metal that rusts away before iron. In this figure right here, you can see that the iron nail on the top is connected to the zinc. Right, this is zinc. And zinc rusts away before iron, like I said. So you can see that the iron nail with the zinc on top of it doesn't rust. But the one without zinc, what happens? You see it rusts, right? So that's also another way to protect iron from rusting. Okay. So now let's take a look at this question here. Tell me which of the following metals are suitable for cathodic protection of an iron object. I gave you, for example, zinc, aluminum, tin, and copper. Well, can you use zinc for cathodic protection of your iron tank or structures? Can you use zinc? Of course you can, right? As I mentioned, if you go back to look at the EMA of zinc compared to iron, the zinc half cell will have lower EMA than the iron ones, right? So zinc will rust away far before iron. So that's good because you want something to rust away before iron, right? Aluminum is the same thing. When you look at that table, aluminum also has far lower EMA than iron. So that works too, right? So aluminum will rust away before iron does, right? Same thing. What about tin? What's the EMA of the tin half cell? Can you tell me? What's the EMA of the tin half cell? 0.1 something, right? Compared to one with iron, which is 0.44. Which one will rust before which? Iron or tin? If you put them together, which one will rust first? No, it's iron. Why? Because iron has lower EMA than Sn, right? One is minus 0.1 something, but iron is minus 0.4 something. That's lower, right? So if you put irons along with tin, so iron will rust, tin won't rust at all. Tin will just stay like that, letting iron rust away happily. And you don't really want your iron to rust, right? What about copper? If you connect your iron with the copper wire, which one will rust first? Of course, iron. Why? Because the EMA of the copper half cell is plus 0.34 volts, right? That's much higher than the one for iron, which is minus 0.44 volts. So in that case, iron will also rust away before copper, right? So that's how you apply this knowledge when you compare EMA of each half cell and figure out which one you should use to protect your iron structures. Okay? Any questions? All right. The last topic I want to cover for today is electrolysis, right? So we spent time talking about galvanic cells, which are spontaneous electrochemical cells, right? But now it's something completely different. Electrolysis is a process where you pass in electrical currents into the system to drive a non-spontaneous, the keyword is here, to drive a non-spontaneous reaction, right? So any electrochemical cells that fits this criteria will be called electrolytic cells. So this is the keyword, right? So when you see this keyword, electrolytic cells, you can know for sure that, oh, the reaction is not spontaneous, right? Because you need to put in external energy to make it happen, right? So in this type of cell, EMA of the cell or E cell will always be less than 0 because the reaction is not spontaneous to begin with. Okay? The example here is the electrolysis of sodium chloride. Okay, so let's suppose you have your tables of sodium chloride and you heat to very high temperature around 800 degrees Celsius, sodium chloride will melt. Okay, so basically, when your sodium chloride is melted at maybe 800 degrees C, so you can put in the electrodes, right, and pass in electricity. So after you pass in electricity, what happens is that the sodium plus iron will get reduced at the cathode, right? Sodium plus iron got reduced at the cathode to become sodium metal, right? And then in your molten sodium chloride liquid, you have the sodium ion and chloride ion floating around. So the sodium ion will gather around the cathode and give it use. Whereas the chloride ion, which has the minus charge, will gather around the anode and loses the electron. Right? Cl minus loses the electron and eventually become Cl2, the chlorine gas. Okay, so you get chlorine gas at the anode and you get the sodium metal at the cathode, right? So this is a reaction right here. So you drive this reaction from a non-spontaneous process to make it happen. 2 moles of sodium plus in the liquid phase plus 2 moles of chloride ion in the liquid phase. Those 2 moles of liquid sodium metal and 1 mole of chlorine gas. Right? Actually, what is spontaneous is when you react sodium with chlorine gas. That's the spontaneous one. So the reverse reaction is not spontaneous by nature. But this can happen because you pass in electrical currents to make this reaction occur. Okay? This is a type of an electrolytic cell because you use that to separate sodium, metal, and chlorine gas. Okay? Another application is that you can also use this type of cell to perform electrolysis of water. Okay, so when you do this thing, electrolysis of water, you get hydrogen gas at the cathode and you get oxygen gas at the anode, right? The net reaction is that you have 2 moles of liquid water being decomposed into their constituent elements. So you have hydrogen gas at the cathode and you have the oxygen gas at the anode, right? So how do I know which one is oxygen, which one is hydrogen? If you study about ideal gas, so you can see that since there will always be twice as many moles of hydrogen as oxygen, so it occupies about 2 times more volume as well, right? So I can know that this side is my cathode, right, where the oxygen form. This side is my anode, which is where the oxygen form. Okay, so one caveat here is that this solution needs to conduct electricity, right? So you have to have some salt in this solution, otherwise water is a very, very bad electrical conductor. When electrical current won't pass through just your water alone. So you need some electrolyte solutions in there. Normally, we use sodium sulfate or sulfuric acid as an electrolyte solution. Well, you may ask, can I use sodium chloride as my electrolytes? Sodium chloride also dissolves completely water, gives me ions. Well, yes, they give me ion in water. But what happens when I put in sodium chloride instead of sodium sulfate? If I do that, I won't get oxygen at the anode. I will get chlorine gas instead. Why? So let's say if I put in sodium chloride as an electrolyte instead of sodium sulfate, when I pass electrical current into the water with sodium chloride, I won't get oxygen at the anode. I will instead get chlorine gas at the anode. Why so? Let's go back and have a look at that table here. Okay? So for this to just go back. Okay? Take a look at that. Okay, now we are back with this table. Okay? So you can see here that the half cell that involves at the anode of that electrolytic cell is this half cell, right? What about the one with chlorine? Well, is this half cell, right? These are the reduction half cell, right? But we want to talk about the oxidation. So which one will occur first? Well, since we talk about the electrolytic cell in that case, so the rule will get reversed, right? Had we talked about galvanic cell, then you know, oh, this thing will be the anode, the oxygen acid should be the anode. But now we talk about the electrolytic cell. This is no longer the case, right? This thing will happen before, will be the anode in the electrolytic cell. So when you talk about electrolytic cell, it will be reversed. What tends to happen at the anode will be the one with higher EMA, right? So in that case, you get the chlorine gas because the chlorine cell has the higher EMA compared to the oxygen cell in the electrolytic cell. So you get chlorine gas instead of oxygen. Well, what about the sulfate? Why can I put the sulfate without affecting this? Well, let's see if they've got the sulfate. Okay, so if I put in sodium sulfate, so you can see that the EMA involving the sulfate ion is down here, right? So compare the sulfate half cell to the oxygen half cell. The oxygen half cell has higher EMA, right, in the electrolytic cell. So this is something that will take place before the sulfate before sulfur dioxide being oxidized into sulfate. Okay, so that's why you get oxygen instead of the sulfate. That's why you use sodium sulfate salts to perform electrolysis of water, not sodium chloride. Okay, so that's the reason that we use some specific kind of salts. Okay. And then the last topic that I want to cover for today is about the stoichiometry of electrolysis, right? So basically, when you have a reaction involving electrolysis, the number of electron transfer in 1 mole of reaction can also be used in stoichiometric calculations as well. So before that, there are things in physics to consider before you can calculate the moles of the electron, right? In physics, you know that there are electrical currents, which is in the unit of amperes, right? And then you also have the elapsed time once you pass in electrical currents, right? When you want to calculate the charge, which is in coulomb, right? In physics, we normally express the charge in the variable Q, right? Which is in coulombs. Q equals the current multiplies with the time, right? Q equals I times T, right? Coulomb, the unit coulomb is just amperes times second, right? Coulombs is ampere second. So basically, when you want to convert the current into coulombs, you need to convert the unit of the current into just amperes and convert the time into seconds. So you can multiply the current and time together to get the charge in coulombs, right? And then you can convert the charge into number of moles of electron through Faraday's constant, which is 96,500 coulombs per mole of electron. Okay, so that's how you relate all these terms and time into the number of moles of electrons. Okay. So let's take a look at some example here. In a certain electrolysis experiment involving aluminum 3+ ions, 60.2 grams of aluminum is recovered when a current of 0.5352 amperes is used. How long did the electrolysis last? Okay, how do I calculate? Well, we know that aluminum 3+ has to accept 3 electrons to become aluminum, right? So there are 3 moles of electrons involved in this reaction. So you can just use stoichiometry to convert the moles of aluminum into moles of electrons, right? Well, how do you do that? Moles of electrons. equals to 60.2 grams of aluminum times, what's the toughness of aluminum? Aluminum is 27 grams per mole, right? So now I have moles of aluminum. And then I have to convert moles of aluminum into moles of electrons, right? So you can just use your simple stoichiometric relationship right here. Now I got it to be some number. I'll leave that out for now at the moment. So this is the number of moles of electrons that actually reacts with aluminum 3+ to get this much aluminum, right? And now I want to convert this into time that actually used in this reaction, right? So charge of electrons in coulombs equals to this 60.2 times 3 over 27 moles of electrons times 96,500 coulomb per 1 mole of electron, right? This thing is essentially Faraday's constant for F that we used in the previous lecture. Okay? So now that I got the charge in coulomb, right? So the charge in coulomb is the electrical currents 0.352 amperes times the time in second, right? This is something I don't know at the moment. I can solve this equation. So I divide the left-hand side by 0.352. So I get the times in second that actually elapsed, right? So what's my answer? Let me figure this out. Okay, so this thing becomes about 1,800,000 seconds, right? But the problem asks in minutes. Okay, so how do I compute that? Okay, so I just divide that by 60, right? So that's 30,562 minutes. That's quite a long time, right? Because we use a lot of small currents. Normally, when you do electrolysis to get metals like this, the current is much higher than this. Okay, this is just too small. That's why it takes about 30,000 minutes just to get 60 grams of aluminum. Okay, any questions? Okay, last problem for my part of the course. Now, you can rest assured on Monday you will see my face again, ever. Okay, now, last one. An aqueous solution of platinum salt is electrolyzed at a current of 2.50 amperes for 2 hours. As a result, 9.09 grams of metallic platinum are formed. So I want to calculate the charge on platinum ions in this solution. Well, I don't know the charge, but I know it exists as a positive charge. So platinum N+, I don't know what N is for now, plus N moles of electrons goes to platinum, right? I want to find what this value of N is. How do I find out? Well, charge involved charges involved in Coulomb is equal to I times T, right? I is the current in amperes times the times in seconds. I have to convert this hour into seconds, right? 1 hour has 3,600 seconds. So that's how I convert this into seconds. So I'll just leave that number for a moment. That's charge in Coulomb. Okay. So now I want to convert the moles of electrons for this charge. It's going to be this. This is just the value of n that I want to figure out. Okay. So is this number in Coulomb times 1 times 96,500 Coulomb per 1 mole. Okay. So that's the number of moles of electron. That's not the energy figured out yet. So that's just the moles of electron involved in this. Okay. We'll figure out that out later, and we work this number out to be what? So this thing is about 0.0933 moles. That's not our answer yet, okay? Because this much moles of electron resulted in 9.09 grams of platinum form, right? So I have to use my glucose line geometry to get this out. So 0.0933 moles of electrons times n moles of electrons, right? Because we have the n here goes to 1 mole of platinum. So on this side of the equation, I already have moles of platinum equals to what? 9.09 grams of platinum. Convert this into mole. What's the atomic mass of platinum? It's actually a lot. It's 195 grams of platinum per 1 mole. So I have moles of platinum on both sides. So essentially 0.0933 over n equals 9.09 times over 195. So from this equation, I know that n will equal to 0.0933 times 195 over 9.09, which is 2. Well, it's 2 point something, but this n should be an integer, so it's 2. Okay, so the charge of platinum is 2. That's the answer, it's 2. Okay? So I did that by computing the charge in Coulomb first, and then converted the charge in Coulomb into moles of electrons. And then you just use that number of moles of electron, just like in regular cyclometry. Okay, and then I found out that the value of n I didn't know from the first moment to be 2. So the charge of platinum involved was 2. That's the answer. Okay? Any questions? Right. So now, here are the summary of concepts I will talk about now in no time, so you should do that yourself in the slides. And of course, that's the end of my part of the course. So the final exam on my part will cover from lecture 5 onward to this lecture. And I will give you the exercise on those parts very soon. Okay, I will announce that later on Microsoft Teams. Not from this Thursday, and of course from next Monday. You will be with Ajahn Gilapa for the rest of the course until the final exam. Okay? Excited? And now you want to see my guest gamer again. Maybe on time you see well, but after that you want to see for the rest of the course till the final. So I wish everyone good luck for the rest of the time in Chiang Mai University. I wish you a very, very happy, healthy, and wonderful the rest of the semester. Okay? I'll see you guys around. And of course, hopefully I'll see you in the next semester because I will be teaching the next course to this as well. So I will be here next semester. I hope to see you there too. Please survive. Okay? Okay, see you around. Have a good weekend.